All right, welcome to this lesson on voltaic or galvanic cells and the electromotive force. Just a quick note that voltaic and galvanic cells are the same things and can be used interchangeably. So, electrochemical process is basically the conversion of chemical energy into electrical energy, and this is the basis for all batteries that we use, regardless of whether they power a cell phone, an AED, a car. They all work on this kind of spontaneous electrochemical process. So a galvanic cell is it's basically two half reactions. They occur in a separate vessels, and they're connected in by a wire. Now, again, one of these half reactions is going to be oxidation, aka they're losing electrons, and the other reaction is going to be a reduction. So if we have our oxidation and reduction, they're connected to by a wire here. And so what's going to happen is, because this side is going to be losing electrons, the electrons that are lost are going to travel through the wire, go off to the other one, which powers the reduction potential. So they're going to gain here, they're going to lose here. And because of this movement of electron, you'll be able to create some work, aka we'll be able to power our electronic devices. So a half cell is basically a metal in its own solution. So for example, if this was copper metal, which it is, we have copper solid, and inside we have copper 2 plus, let's erase that there. We have copper 2 plus ions in here. And so it's a simple half reaction. What's actually happening is you'll notice that there's going to be an equilibrium established. So some of the copper metal is going to form into solution ions, or into ions, and some of the ions will form into copper. So there will be an equilibrium, which means that it's not static. It will continue to go, okay? But you'll see that there's no net change. Okay, so there's still going to be reactions happening, but you won't see a visible difference. So that's a half cell. When we connect two half cells by a wire, we get something awesome. We get the movement of electrons. So this is a hydrogen half cell. This is, again, we were talking about before. It was our kind of served as our standard in our standard reduction potentials. But what you can see is this is a beautiful picture to highlight what's actually going on. If you look at this part over here of the diagram, you can see two things happening, which if you don't look close enough, you might seem as one thing. But in the first top here, we have hydrogen gas going onto this platinum electrode, and it is losing these electrons. So it's going from H2 into 2 hydrogen protons plus 2 electrons. So in this case, what we're happening is we're having an oxidation reaction. But just below it, what we're seeing is that these H plus are picking up these 2 electrons and reforming the H plus. So we're having 2 H plus aqueous, picking up those 2 electrons to create H2. And so what happens is that this reaction keeps happening back and forward. It's an equilibrium reaction. So it happens, but again, you won't see any net change. So that's just a half cell. It doesn't really matter unless you have something else attached to it. And so if we put two half cells together, what we're going to see is that we're going to see some kind of reaction. Now, in this case, one will always be oxidized and one will always be reduced, which means that all of these reactions in galvanic and voltaic cells are spontaneous. Okay? So in this case, we have to figure out which one is being reduced. In this, where we're looking at zinc and copper, we have to figure out which one is going to be reduced. And so what we look to is yes, to our standard reduction potential table. Now, once we see that Cu2 plus is higher than zinc, so it's going to be the oxidizing agent. The Cu2 plus is going to be our oxidizing agent, which means it's going to be reduced. Alrighty, so in this case, our oxidizing agent is right over here. So what's our half reaction going to be? Well, if Cu2 plus aqueous is going to be reduced, it means it's picking up 2 electrons and forming Cu solid. That means our reducing agent, the one that is our reducing agent, the one that is going to be oxidized or losing electrons, is going to be our zinc. So our zinc solid is going to break down into Zn2 plus those 2 electrons. Now how this is going to work is that here we have our zinc metal, and it's going to lose 2 electrons into this metal here. It's going to be deposited onto this metal, and it's going to form our zinc 2 plus, which is going to go into solution there. these electrons, these two electrons, are going to move through the wire and be deposited here. Here are two negative electrons, just kind of by our negative signs. So there's going to be Cu2 plus ions in here, aqueous. They're going to pick up those two electrons and actually form little Cu deposits on the edge of the metal. So eventually what's going to happen is that one of these electrodes is going to actually start getting smaller and smaller and smaller in size, while the other one's going to get bigger in size. Can you figure out which one? If you said that the zinc is going to get smaller, you're absolutely right, because the metal is being converted into an ion. These electrons are moving over this side, and in this side, the ions are being converted into a metal and depositing on this electrode. So eventually the reaction will stop. How come? Well, what's actually happening is that as this reaction happens, there's going to be more zinc turning into zinc 2 plus on this side. So this side is going to get really positive. While on this side is going to be really negative, because all the Cu2 plus is going to form here, which is going to be leaving whatever ion it was. So for example, CuNO3 minus 2, sorry, not the minus, but CuNO3 2. Once this goes into solution, it becomes your Cu2 plus, which we have over here, but it also becomes the NO3 minus, and there's two of those. So if all of the Cu2 plus that is being made here is being taken up and converted into Cu metal, what's left? Well, all the NO3 minuses are left. So this side is becoming very negative, and this side is becoming very positive. Now, why does this actually really stop? Because remember that electrons travel through a potential difference. If this side that they're traveling to is becoming really negative, and remember that the electrons are very negative, what do two negative things do? They repel. Okay? And so what that's going to do is that the electrons will not want to travel there anymore. It's not going to come down this way anymore, and so the whole reaction will eventually stop, because Cu is saying, nope, sorry, I can't accept any more electrons. So that means that the zinc can't give off anymore. If no one's accepting them, they can't lose them, and so the reaction will eventually stop. So how do we prevent this? We obviously know that batteries keep going for a while. How do we prevent it? We use something called a salt bridge. And a salt bridge is basically a tube, as you can see in the diagram here. It's just a tube here that we put into both solutions, and we fill it with some kind of aqueous solution. On the end, we put either cotton or kind of gel, and we put into the solution so that the two solutions don't actually mix, but you do allow for ions to be switched either there, in that direction, or in that direction. So in this salt bridge, we usually use things like potassium nitrate, so it would be formed into K plus and NO3 minus. So the side that would become positive from this movement of electrons, the nitrate would move into that side and try to neutralize that charge, and if the side become negative, the potassium ion would go in there and try to neutralize that charge. Therefore, this reaction can keep going, and electrons can keep moving from one side to the other. So these are the parts of our voltaic or galvanic cell. We have our two half cells. So in this case, we do have this half cell over here, and we have the other half cell over here. They're connected by a salt bridge right there, and we have a wire. Usually in that wire, we have a voltmeter or a load, some kind of light bulb or something like that to show us that it's working. But the voltmeter is usually what's most used because it shows us the potential difference. The side where oxidation occurs, so aka they are losing electrons, okay, so we're going from a metal into its ion, aqueous plus an electron. What we're doing is that will be called our anode. Okay? And the opposite side, the side where you're going and the electrons are going to here, this is our reduction, so B plus an electron turn to be solid. That is going to be our cathode. So they do have charges assigned to them. Electrons, they flow from the anode. They're negative because the electrons kind of are built up there, and they move to the cathode, which is positive. That's where the electrons are being gained. The cathode does not mean positive, the anode does not mean negative. This changes with electrolytic cells. So just for voltaic cells, the anode will be negative and the cathode will be positive. There's a little diagram here, red cat and an ox. So this kind of helps us remember what's happening on each. So in a cathode, you're going to have reduction. On the anode, you're going to have oxidation. Okay. Let's just take a second just to read the descriptions there for anode and cathode. All right, so this is a pretty loaded diagram, but it very nicely describes what is actually happening. So in this case, we have two half reactions. We have our zinc half reaction, our half cell, and our copper half cell. So it's a copper metal in its own solution. Again, 1 molar, it's standard. And we have zinc metal in 1 molar of solution. And so in this case, one of these is losing, one of these is gaining. And because zinc is the stronger reducing agent, it will be oxidized and lose its electrons. These electrons go through a voltammeter and then go to the other half cell. Now you can see that the potential difference is positive 1.10, so it is positive, which means that it is a spontaneous reaction. And we said before that all of these galvanic and voltaic cells are spontaneous reactions. So here what we can see is in our overall cell reaction, we get that from our two half reactions. We know that zinc is being oxidized, it's losing its electrons, so there's our half reaction there. And copper is being reduced, so it's picking up those two electrons. So if our electrons are already balanced, our overall cell reaction will be this. And as you can see from these little diagrams here, zinc is going from metal and depositing into solution, losing its electrons onto the actual metal. What that's going to do is it's going to deposit on the metal, go through the wire, and go to the other side. Once the electrons get onto the actual electrode, the Cu from the solution is going to come in and form a copper deposit on the metal. So from the little diagram on the side here, what you can notice is that the zinc electrode loses a lot of mass and the copper gains mass because it's taking Cu2 plus out of solution and depositing it on the surface of the actual metal. Now, instead of drawing this whole this whole diagram, we can use a cell shorthand. And so in the case of the reaction between copper and zinc, what we need to figure out is, again, which one is being oxidized and which one is being reduced. And from the previous example, we saw that our zinc, because it is a stronger reducing agent, and we can figure that out based on our standard reduction potential, is that it's going to be losing electrons. So we always put the reactants before the products. And in this case, we have our metal here, and we have our aqueous solution there. And these little lines over here, the one lines represent a phase change. So this is solid, this is aqueous, so it's the different phases, so we separate that using a line. Same thing with this. Here are our reactants, here and here, and these are our products, here and here, which is why we say always put the reactants before the products. And we always put our oxidation on the left and our reduction on the right. This little double line here represents the salt bridge. It's not important to actually show what the salt bridge is, just that there was one there. So in this example, here we have cobalt and aluminum. What I'd like you to do is deduce the half reactions and figure out the shorthand for the cell shown here. Okay, so try to take a couple of moments. We'll take it up in a few moments. So just pause the video now and work on it. Go ahead and pause. All right, so in this case, the aluminum is lower than the CO in the standard reduction potential table. So aluminum is the stronger reducing agent, so it becomes oxidized. So our oxidation reaction is going to be aluminum solid, and that's going to break up into Al3 plus aqueous plus 3 electrons, and our reduction is going to be CO2 plus aqueous plus 2 electrons to create CO solid. Now again, we'd have to multiply these by a certain factor to get our overall equation, but that's not our goal right now. Our goal is to simply figure out what the shorthand is going to be between here. So those are our two half reactions. The one that is being oxidized is aluminum, so we're going to put that here first, solid, and we're going to have our phase change. We'll get Al3 plus aqueous. We use the salt bridge. In this case, not drawn here, but there will be a salt bridge in there. And then we have our CO2 plus aqueous plus our CO solid. Again, just to remember that our reactants go before our product. So in this case, our reactant is Al, and it produces Al3+, which is why it goes second. And in this case, the order is reversed because our reactant is CO2+, and we produce CO solid. So it's going to be a little bit reversed there. Okay? And so that is our shorthand for this reaction there. Now, if you wanted to do it, you could calculate the E cell, which we'll be doing a little bit later. So for these reactions, look at your standard potential, and our E cell for this reaction is positive 1.38 volts. So we see that it's a spontaneous reaction. So for this little practice session, what I'd like you to do is just label the following. So the reaction between magnesium and gold, label the cathode, the anode, the area where oxidation reductions are taking place, is the sign convention. So what sign is the anode, what sign is the cathode. The salt bridge, you don't necessarily have to show what it's made out of, just salt bridge. The half reactions for each of the half cells, the direction of electron flow, and the shorthand notation of the cell. So pause the video right now and go ahead and label. You can print off this worksheet. It's online. It's just called a blank. So you can print that off and use it as your practice. So go ahead and pause the video. All right, so welcome back. Take a look at these videos. So you just pause and play. So pause this video, open up these ones on your YouTube, on your own browser, and watch them. They give you some good visual looks of how it actually works and what the process is. So watch both of them and come back when you are done. All right, as mentioned, these galvanic and voltaic cells, they're electrochemical cells, and they always work through a spontaneous reaction. So regardless of what half cells you hook up, the stronger reducing agent will oxidize and therefore force the other one to be reduced. So regardless of what you form, obviously if you hook up the same half cells, then there's not going to be any potential difference. So for example, if you hook up a copper half cell with a copper half cell, there's no potential difference and there won't be any movement of electrons. But as long as one's going to be stronger than the other in terms of its ability to be reduced or oxidizing agent, then there will be a reaction and it will be spontaneous. So again, this difference in potential is called many things. It can be called cell potential, E-cell, electromotive force. I've highlighted force because there's no actual force being applied, but it's just the movement of electrons, kind of the electrons pushing on one another and forcing them to keep moving. So it's under constant conditions, it's related to the ability of something to lose electrons and therefore force the other one to gain electrons. So there is a potential difference between the two different electrodes, and so that potential difference that we actually kind of calculated before is called our E cell. Now when we calculated E cell to look at spontaneity, and we just looked at its sign, but if we actually take into account the number that's attached with the sign convention, that is actually our E cell in total. So in this case, let's calculate the EMF for the following cells. So we know that because this is on this side, this is going to be our oxidation, and this one is going to be reduced. So in this case, if we write out our reactions, we're going to get Na solid producing Na plus an electron, and we'll get on the other side of being reduced, Fe2 plus is reduced, it picks up 2 electrons to be reduced into Fe solid. Now we can see, if we look at this is our E oxidation, and that's going to be positive 2.71 volts, and this is our E reduction, which is going to be equal to negative 0.44 volts. What we notice is that our electrons are not balanced, so we need to multiply these by a factor. I'm going to multiply that by 2 and that by 1, which really means we don't really have to do anything with that. Once we get that, we can cross out our electrons, and we will be left with 2Na solid plus Fe2 plus aqueous, and that will produce 2Na plus, 2Na plus aqueous plus Fe solid. Now to get our E cell, we add these up and we get positive 2.27 volts. So not only is it a spontaneous reaction, we get 2.27 volts, which ain't that bad. So just a quick note again, just because we multiply to balance our electrons, we never multiply the reduction potential. It's intrinsic, so it doesn't really work in the same kind of convention. So go ahead, look at this reaction between magnesium and zinc. Which one would be the anode, the cathode? Which way would the directions flow? What would be the overall reaction equation? The shorthand, the E cell, and do the same thing for zinc and Fe, and we'll come back. Alright, so here are the answers for the magnesium and zinc reaction. Try your hand at the other one as well. So again, you take a look at that, and that's the end of this lesson. See you next time.